Okay, so hello and welcome back. So the next question that we have here is question number 7. Question number 7, which is basically consider the function f. Consider the function f from R to R defined by f of x is equal to 4x plus 3. Now show that f is invertible. You want to show that f is invertible. F is invertible, and then of course then find the inverse of f. Okay, now in order to solve this problem, we need to basically, what we can do is that basically to show that f is invertible, that f is invertible, you need to show that there exists a function, for example g from R to R, and of course you have to swap the codomain and the domain, but in this case basically the codomain and domain are the same set, so you would get the same thing. Otherwise, if f was, for example, from n to R, then you would get the inverse of that as g as R to n, right? So then you need to show that there exists a function g from R to R such that basically g of f is equal to I of basically x, and x meaning that the identity function on the domain of f, and also f of g is equal to I of y, which is basically the identity function on the codomain of f. So we need to show that if we can show that there exists a function g from R to R such that g of f is equal to I of x, and therefore g is equal to I of y, then in that case g is the inverse of f, right? So that's what we need to do. Now in order to do that, what we can do is that we can define a function Now before we do this, what we need to do is first we need to make sure that f is invertible in the first place, because you could actually go through this whole process, and if f is not invertible in the first place, then you have done this whole thing for nothing, right? So That is number 1. Now, before doing number 2, before basically doing number 1, you need to make sure that f is invertible in the first place. Invertible in the first place. In the first place, otherwise you might do number 1, and in the end of the process come to the conclusion that the function that you have found is not the inverse of f. Is not the inverse of f, simply because f was not invertible. Was not invertible in the first place. Right? In the first place. So if I can make sure that f is not, so if I know that f is not invertible in the first place, of course I would not start with the process. That doesn't make any sense to start with the process only to find out in the end that f was not invertible. That's a lot of unnecessary work to do. So what that means is that now number 3, in order to do 2, you need to make sure that f is 1 1 and onto, meaning that f is basically injective and surjective, or in other words you can say that f is basically bijective, right? If that is the case, then basically f is invertible, right? So now let's start with basically with this part which we want to find out whether f is 1 1 and onto, or injective and surjective. Now to check whether f is injective, you need to make sure, basically, in f being injective, meaning that every distinct element of the domain has a distinct image has a distinct image in the codomain of the function, which means that basically, okay, so now basically to check whether basically to check whether f is injective, basically the condition that we use for f being injective is that we say that basically f is injective if every basically distinct element of the domain of the function, meaning that if this is the domain of the function, call it x, and this is the codomain of the function, call it y, every distinct element of the domain of the function must have a distinct image in the range of the function, meaning that this is mapped to this element, this element is mapped to this element, this element is mapped to this element, and this element is mapped to this element, meaning that this distinct element of the domain has a distinct image in the range. This distinct element in the domain has this distinct element in the range, and so on and so forth until the last element in the domain. So, or another way of saying the same thing is that if let's call this, for example, x1, and let's call this x2. Now this becomes f of x1. If this is f, for example, if the function is f, this becomes f of x1, and this becomes f of x2, right? Now, if basically if f of x1 is equal to f of x2, meaning that two images happen to be the same, if it happens that there are two images in this set that are the same, meaning that if f of x1 is equal to f of x2, then what that implies is that basically x1 is equal to x2, meaning that there are basically two elements in the domain of the function x1 and x2 that are exactly the same. And so what that means is that then there is only one distinct element in the domain that is mapped to one distinct element in the range, and that is basically the condition that we use. So basically then we write this as for every x1 comma x2 belonging to the domain of the function, f of x1 is equal to f of x2 implies that x1 is equal to x2, right? Which is basically the condition that we use. Now, this condition is now basically I want to prove this for the function f that we have here, and f is a function from R to R, and f of x is equal to 4x plus 3. So f of x is equal to 4x plus 3, and f is a function from R to R. Now, since I want to prove this, of course, this is a conditional sentence. This is a conditional statement, meaning that there is one statement over here, one statement over here, and this is an implication. So you have P and Q, meaning that you have basically P implies Q. Now, to prove a conditional sentence P implies Q, you have to assume that P is true, and then based on that, prove that Q is true. If you can do that, then that means that P then Q is true. If you cannot do that, then that means that P then Q is simply not true, right? So now assume that P is true. That is basically, assume that basically f of x1 is equal to f of x2. Now, in the function that we have, f of x is equal to 4x plus 3. which means that f of x1 would be equal to 4 times x1 plus 3. And f of x2 would be 4 times x2 plus 3. Now these two I can cancel out, and then I can divide both sides of the equation by a factor of 4, which means that x1 is equal to x2. So now here, basically what I have done is that I have assumed that f of x1 is equal to f of x2, and that implies that in this particular case that x1 is equal to x2. Therefore, f is 1, 1, 1, 1, or injective. F is 1, 1, or injective. 1, 1, or injective. The next thing that we want to show is that to show that f is basically onto or surjective. Now to show that you need to make sure that for every, if you have some function, for example, some function f from some domain x to some codomain y, then you need to make sure that every element that belongs to the set y is the image of some element in the domain x, meaning that there is no element in the domain y which is not an image of some element in the set x. So in order to make sure that that is the case, what I will do is that, or what you need to do is that basically I need to find the inverse of the function, and basically the function that I have is basically f of x is equal to 4x plus 3. Now this 4x plus 3, what it does, the domain of the function is the set of real numbers, the codomain of the function is the set of real numbers, and this domain and this f basically, it basically maps these elements to the other elements in the codomain of the function using some rule, using this rule. Now what I need to do is that I need to show that and this rule basically what it does is that it tells me how to get from here to here, right? But if I want to get back from here, if I want to get from here back to here, I don't know how to do it. And it becomes important to be able to get back from here to here, because I want to make sure that every element that I have here is the image of some element in the domain of the function. Now, if I can make sure that from each and every element in this set I can get back to some element in this set, then I can make sure that every element in this set is the image of some element in the domain of the function, and that means that the function is onto. That's the definition of the function. The definition of being onto, or the meaning of being onto. So what that means is that now I need to find a way to get back from here. I need to get back to the first function I originally came from, right? Now I can basically find how to get back using the same rule using which I started my journey in the first place. So this tells me how to get from here This tells me how to get from here all the way up to here. So since I know how to get there, I can use the same rule and change it back and find the inverse of that so that it tells me how to get back, right? That's basically why we find the inverse of the rules of these functions when we want to know if we can actually get back from each element of the codomain to some element in the domain of the function. So what I'm going to do is that I'm going to assume that, first of all, I know that f of x is equal to 4x plus 3, right? So then I'm going to assume that I'm simply going to assume that basically f of x is equal to some y, for example. So if f of x is equal to y, this becomes y is equal to 4x plus 3. And if I find x in terms of y, what that means is that this tells me that basically 4x is equal to y minus 3, or x is equal to y minus 3, or x is equal to y minus 3 divided by 4, which means that this gives me a relationship between x and y. So y is basically originally the output of this function, which is f of x. So this f of x is basically y. And this x is basically the input of that function. So now what this tells me is that, what this relationship tells me is that I know that basically I know that every x that I can find in the domain of the function, let me show you what that actually exactly means. So if I say that y is equal to, let's say that these are my x's and these are my y's. So when I write y is equal to 4x plus 3, that tells me that each y that I can find over here is equal to basically some x that I can find in this set, multiplied by 3, and then add 3 to that, and that is equal to this y. Now if I write basically x is equal to y minus 3 divided by 4, what that means is that every x that I can find in this set, that is actually equal to some y that I can find in this set, subtract the 3 from that, and then divide the whole thing by 4. Which means that basically every y that I can find over here, I can get to that using this rule over here. Meaning that if I write f of basically y minus 3 divided by 4, if I calculate this based on the rule of the function, I can write this as 4 times basically 4 times x plus 3. So I substitute the x with this input. This becomes y minus 3 divided by 4, and add 3 to that, right? So these two will cancel out, so you have y minus 3 plus 3. These two will cancel out, and you will get a y. Meaning that every y that I find in the range of this function, I can get to that if I input y minus 3 divided by 4. So in short, what it means is that In short, what it means is that f of y minus 3 divided by 4, in the case of this particular function, is equal to y, right? Now I just need to make sure that every element in the set y is covered through this relationship, meaning that any y that I pick in the codomain of the function, I need to be able to basically to get back from this y to some y minus 3 divided by 4. Now over here we said that f is a function, basically previously we said that f is a function from R to R, right? So that means that this y that I can find over here belongs to the set of real numbers, and so I can assume that y is a real number, right? Now, in order to get back from this y to some pre-image in the domain of the function, I need to use this y minus 3, meaning that if y has to be the image of some element over here, that element has to be y minus 3 divided by 4. Now, if I can make sure that basically y minus 3 divided by 4 belongs to the set of real numbers, then of course over here I have all of the members of the real numbers here at my disposal, and so I can use each and every one of those members of the set of real numbers to get to any y that I might have in the set of in the codomain of the function. Now if I imagine that y is a real number, then y minus 3 is a real number, and if I divide the whole thing by 4, that's again going to be a real number, and a real number actually does exist in the set of real numbers, which means that you can say that for every y, you can say that for every y belonging to the codomain of the function, there exists an x in the domain of the function such that f of x is equal to basically f of, well, you can say f of x is equal to f of y minus 3 over well, actually I shouldn't write f of x here, that would be logically wrong, such that f of y minus 3 divided by 4 is equal to y, and therefore f is surjective, right? So now that we have made sure that f was, basically we showed here that f was injective, and over here we have showed that f is surjective, we can say that therefore f is injective and surjective, therefore f is bijective, and the inverse of f exists, And now that we know that the inverse of f exists, we can actually find the inverse of f. So let's go up here. So basically, 2, we said that before doing 1, you need to make sure that f is invertible in the first place. Otherwise, you might do 1 and in the end of the process come to the conclusion that the function that you have found is not the inverse of f. Simply, there's an f over here, simply because f was not invertible in the first place. And then we said that number 3, in order to do 2, you need to make sure that f is 1, 1 and onto, which we already did. So now we need to go back to 1 and do step number 1. Which is basically, we said that to show that f is invertible, you need to show that there exists a function g from R to R, such that g of f is equal to I of x and f of g is equal to I of y, right? So now the step number 1. So step number 1, now we need to show that, there exists a function g, there exists a function g which goes from R to R, such that g of f is equal to I of x and f of g is equal to I of y. Now we will show this one. Okay, so now in order to show this part, you can argue that, for example, let g as a function from R to R exist, for example. Now we will define g as basically f of g of y is equal to this function. Let's see if we can actually use this function here, y minus 3 divided by 4. And the reason is that basically you can imagine that you know that f of x is equal to function f is basically 4x plus 3. 4x plus 3. Now if I set f of x is equal to y, then y is equal to 4x plus 3, which means that 4x is equal to y minus 3, which means that x is equal to which means that x is equal to y minus 3 divided by 4. And so this is actually the inverse of the function that we have here, meaning that for example, suppose that this function is a function from R to R. So suppose that I input into this function a 1, for example. Over here f of 1 is going to be equal to 4 times 1 plus 3, which is equal to 7. Right? Now if I give this 7 to this function, if I actually define this as a function, if I say that this function, call it for example g of y, and call it basically y minus 3 divided by 4. Now if I calculate g of 7 here, g of 7 here, that gives me 7 minus 3 divided by 4, which is equal to 4 divided by 4, which is equal to 1. So you see, this function gets me from 1 to 7, and if I input this 7 into this function, if I input my 7 into this function, then this gives me the 1 back that I started with here. It's like a cycle, right? So that means that g of y is the inverse of this function. Now, so based on this, we can say that we will define g as g of y is equal to basically y minus 3 divided by 4. Now we need to show that basically g of is equal to I of x, and FOG is equal to I of y, so that we can prove that, prove that basically g is the inverse of f. So now GOF, basically GOF of x is the same thing as g of f of x, which is equal to, well, g of y is equal to y minus 3 divided by 4. And we know that basically, we also know that f of x is equal to 4x plus 3. We know that f of x is equal to 4x plus 3, I suppose, right? Plus 3. 4x plus 3. So then g of f of x would be basically, in g of y, wherever you see the variable, you have to replace that with the whole function f of x, which means that I can write over here 4x plus 3 minus 3 and divide that by 4. These two will be cancelled out, you'll be left with x. And x is basically the variable that comes from the domain of the function, which means that any x that you input into this function, it's going to give you x, which means that basically GOF is actually the identity function on the domain of f. This means that GOF is the identity function on the set that is the domain of f, right? Now we need to also make sure that FOG is equal to I of y. So FOG is equal to FOG of y is equal to f of g of y, which is equal to now g of y is basically this function here. This is g of y, and this is f of x. Now in f of x, wherever you see the variable, you have to replace that with g of y. So I can write 4 times this function, which is y minus 3 divided by 4 and plus 3, and then these two will be cancelled out, these two will be cancelled out, and you'll be left with y, which means that now y is basically the variable that we define to be the same thing as f of x, meaning that it is related to it is a member of a typical member of the codomain of f, which means that any y from the codomain of f that you give to FOG, it will give you the same thing back, which means that FOG is the same thing, is the identity function on the set, which is the codomain of f, right? So now that we have shown that g of f is equal to I of x and FOG is equal to I of y, therefore basically g is the inverse of x. So that was question number 7. Okay. Now let me take a look at the solution here as well. Exactly like that. Okay. Now in the next video we will talk about question number 8. I'll see you in the next video, and thank you.